All right, let's jump right in. Today, we're going to be detectives. We're solving a classic physics mystery, the case of a drifting boat on a seriously powerful river. We'll use some logic, a little bit of geometry, and of course, vectors. And our main clue? It comes from one of the most legendary physics problem books out there, i.e. Irodov's Problems in General Physics. Let's crack this thing open. So here's the mystery we need to crack, straight from problem 1.9. You've got a boat, but the river it's on is moving twice as fast as the boat's engine can push it. Our mission, should we choose to accept it, is to figure out the perfect angle to steer that boat so it gets swept downstream as little as humanly possible. It is all about minimizing that drift. You know, every good investigation starts with laying out the evidence. So our first move is to break this problem down into its core pieces. We need to identify the key players in this whole scenario. First up, the boat itself. It has its own velocity, which we'll call v prime. Think of this as the boat's top speed on a perfectly calm lake. It's the pure power coming from the engine, totally separate from whatever the river is doing. Then, of course, there's the river. Its velocity we'll call v naught. This is how fast the water is moving from the perspective of someone just standing on the shore. This is the big, powerful, external force that's trying to ruin our day. It's the current we have to fight. And finally, what happens when you put them together? You get the resultant velocity, v. This is the actual path the boat takes. It's the real-world outcome of the boat's engine pushing one way and the river's current pushing another. In physics, we call these forces vectors, and v is simply what you get when you add the other two vectors together. Now here it is, the crucial clue, the smoking gun of this entire problem. The river speed, v naught, is twice the boat's own speed, v prime. So this isn't just some gentle stream. The river is a beast. This fact is the absolute key to solving this whole case. Okay, we've got our clues sorted. Now it's time for the next phase of the investigation, visualization. We're going to sketch this whole thing out because seeing how these forces interact is where the magic really happens. Let's start with the biggest force on the board, the river. We'll draw its velocity, v naught, as a big arrow pointing to the right. We'll make it nice and long because we know it's the dominant force here. This is our baseline, the direction the stream is flowing. Now let's add the boat's effort into the mix, v prime. To stand any chance at all, the boat can't just aim straight across. That's a recipe for getting swept miles downstream. No, it has to aim upstream, against the flow. So we'll draw its vector pointing partly across the river and partly back to the left. And remember, this arrow is only half as long as the river's. And here's the outcome. The boat's actual path, its resultant velocity v, is what you get when you add those two arrows together. You take the river's powerful shove to the right, combine it with the boat's push upstream, and boom, this new vector shows you exactly where the boat is really going. Okay, this picture is starting to make sense, but let's refocus. The problem asks us to minimize the drifting, so we have to be super clear. What part of this diagram is the drift? It's actually pretty simple. The drift is just the part of the boat's final motion that's going downstream. It's how much the boat is still moving to the right even as it tries to go across. Our entire goal is to make that little horizontal piece of our final v-vector as small as it can possibly be. We've laid out all the evidence. We've got our crime scene sketch. Now comes the best part, the moment of deduction, the aha moment where we use this diagram to crack the case and find that one perfect angle. So here's the thing. We get to choose where the boat's vector, v prime, points. We can pivot it around, and as we change that angle, that final path, v, also changes. So the question is, how do we pivot our boat's vector to make that rightward drift the absolute minimum? And here it is, the big insight, the breakthrough. As you imagine pivoting that boat vector, the drift gets smaller and smaller until it hits its absolute minimum at one very specific, very beautiful moment when the boat's actual path, v, becomes perfectly perpendicular to the boat's own effort, v prime. This is our aha moment. It creates a perfect right-angled triangle with the powerful river vector, v naught, as the longest side, the hypotenuse. And once we see that beautiful right-angled triangle, the rest is just a little bit of high school trig. It's awesome. First, let's look at that upstream angle. Let's call it theta. The sine of that angle is the opposite side, which is v prime, over the hypotenuse, which is v naught. Next, we plug in what we know from our number one clue. V naught is just 2 times v prime. So sine of theta is v prime divided by 2v prime. That just simplifies to 1/2. So what angle has a sine of 1/2? You got it, 30 degrees. But wait, we're not quite done. The question asks for the angle relative to the stream. Well, that's our 90-degree right angle plus that 30-degree upstream angle. And that gives us our final answer.
We've followed the clues, we've built the case, we've made our deduction. There's only one thing left to do: deliver the final verdict in the case of the drifting boat.
And the answer is 120 degrees. To minimize how much you drift downstream against a current that's twice your own speed, you have to point your boat at an angle of 120 degrees away from the direction of the river's flow. So, what does that actually mean? It means if the river's flowing from left to right, you don't just point a little bit upstream. You have to aim way upstream, a full 30 degrees past pointing straight across. That's what it takes to give yourself the best possible shot at fighting that powerful current.
So, case closed. But you know, solving one mystery often leads to another. We found the angle to minimize your drift. But is that the same angle you'd use to get across the river in the shortest possible time? They're two totally different goals, which means they just might have two different solutions. And that, well, that's a case for another day. Thanks for joining the investigation.